In this video, we solve problem 3.3.6 from Nagle's Fundamentals of Differential Equations, 7th edition. The problem statement says, on a mild Saturday morning, while people are working inside, the furnace keeps the temperature inside the building at 23 degrees Celsius. At noon, the furnace is turned off and the people go home. Then the temperature outside is a constant 14 degrees Celsius for the rest of the afternoon. If the temperature constant for the building is 4 hours, the question is, when will the temperature inside the building reach 18 degrees Celsius? And if some windows are left open and the time constant drops to 3 hours, when will the temperature inside reach 18 degrees Celsius? And then they state the answers in this way, and you're just asked to fill in the blank. It says, if the time constant for the building is 4 hours, the temperature inside the building will reach 18 degrees Celsius about blank hours after noon. And we're asked to round to the nearest tenth. And then they say, well, what happens if you change the time constant to 3 hours? Now, if you're like me, you're probably wondering, what is a time constant for a building? This is discussed in section 3.3 of the Nagle Fundamentals of Differential Equations textbook, where they're talking about heating and cooling buildings. But basically what it is we are applying Newton's law of cooling here. And then we're potentially adding extra terms for heat generated inside the building, or furnace heating, or air conditioner cooling to the differential equation. And then they tell us the definition of the time constant in section 3.3. Now, if you're taking my class, just know that you're not going to have Newton's law of cooling memorized. There will be a sentence in the problem statement that will allow you to state or interpret it as the appropriate differential equation describing the physics in this situation. But here they are expecting you to have read the book, and then assuming that you know all of those things from section 3.3, they're asking you these questions. So let's talk about what the time constant is. Or actually, first, let's talk about the mathematical model that they use for the change in temperature in that building. So if you read section 3.3, they're going to talk about setting up this differential equation. If capital T of lowercase t is the temperature in the building, as a function of time t, and it looks like t is generally being measured in hours because we're asked for our answers in hours here. And temperature, it looks like it's being measured in degrees Celsius. Well, in the discussion at the beginning of the section, they say that the change in temperature with respect to time is a sum of the various terms. One term comes from the difference between the outside temperature and the inside temperature. That's Newton's law of cooling. Newton's law of cooling says that the change in temperature of some object with respect to time is equal to some constant of proportionality times the temperature outside minus the temperature inside. So it's saying that the change in temperature with respect to time is proportional to the difference between the inside and outside temperature. And I think that we all know that that's true. If you have ever taken if you've ever taken your coffee outside in the winter, you know that your coffee, the temperature of your coffee drops a lot faster when you first get outside, when there's a huge difference between the ambient temperature and the temperature of the coffee, than when your temperature is already kind of close to ambient temperature. That's what this says. It says the absolute value of that rate of change is going to be largest when the difference between the ambient temperature and the temperature of your coffee is the largest. Or in this case, when we're talking about this rate of change is going to be largest when the difference between the temperature outside and the temperature inside the building is largest. Now, this constant of proportionality K depends on the qualities of the building. So it might depend on the number of doors or windows. It might depend on how well that building is insulated. but it's not dependent on the inside temperature, the outside temperature, or the time t. It's just a constant. So this term in our differential equation comes from Newton's law of cooling. And if you're saying, how do you know that that's true? That's based on experiment. Newton knew that this was true. Well, we've got this, that's affecting the rate of change of temperature. Other terms that affect the rate of change of temperature are the heat generated inside the building, which we'll denote by H of T, that's the notation used in our book, plus any heat generated or cooling generated by either a furnace inside the building or an air conditioner inside the building. So this H of T is heat generated inside the building due to things like people and lights and machines and things like that that are inside. This is some extra heat or extra cooling that was added by either a furnace or an air conditioner. If you add all of these pieces together, then that's going to give you your rate of change. Of course, U of T will be positive when you're using a furnace to heat your building. If your U of T will be negative when you're using the air conditioner to cool down your building. And H of T is depending on, how many lights are in use. Are you using your stove? How many people are inside? And so on. And then this is just related to that, again, Newton's law of cooling, the difference between the temperature outside and the different temperature inside. And that's multiplied by this constant of proportionality, K, which depends on the properties of the building itself, including things like insulation and doors and windows. Okay, so this is our differential equation. And in general, we might be interested in solving this differential equation subject to some initial condition at some particular time, which we'll call T naught. Our temperature will be a known, capital T naught. And then we might want to solve this IVP. Okay, so that is the mathematical model that we're going to use. If you're in my class, I would tell you that this relationship holds. The time rate of change of the temperature is a sum of the heat generated by the building and the furnace heating the building or the air conditioner cooling the building, and it's also and a term due to Newton's law of cooling, which says that the time rate of change of temperature is proportional to the difference between the ambient temperature and the current temperature. So I would give you all of that in a sentence, and I would ask you to derive this differential equation. Now, most of the time, those are going to be 0, and we're just going to be looking at Newton's law of cooling like this. Okay. So with that in mind, let's look at the problem statement. It says, on a mild Saturday morning, while people are working inside, the furnace keeps the temperature inside the building at 23 degrees Celsius. Okay, so the temperature is initially 23 degrees Celsius. Then at noon, the furnace is turned off. So at noon, U of T is 0. And the people go home. The temperature outside is a constant 14 degrees for the rest of the afternoon. So they're telling us that M of T is equal to 14 degrees Celsius. That's constant. Okay, and that the initial temperature, that's the temperature at noon. And we're thinking of, oh, I'm sorry, guys. I was working with this up here and you couldn't see it. We're thinking of noon as our starting time because of the problem statement down here. It says, if the time constant for the building is 4 hours, when will the temperature inside the building reach 18 degrees Celsius? You might say, relative to what time? This part of the problem statement tells us it's relative to noon. It says, if the time constant for the building is 4 hours, the temperature inside the building will reach 18 degrees Celsius at about blank hours after noon. So they're thinking of noon as our T naught, and we're going to say that T naught is equal to 0 to give it an initial time. Rather than using 12 p.m. or something like that, let's just use T equals 0, 0 hours from noon. Okay, so our initial temperature is 23 degrees Celsius. So at T equals 0, we have 23 degrees Celsius for our temperature. Great. It says at noon, the furnace is turned off and the people go home. The temperature outside is at a constant 14 degrees Celsius for the rest of the afternoon. Okay. And what else? The question says, if the time constant for the building is 4 hours, we need to interpret that, and I'll interpret that for you in just a moment. It says, when will the temperature inside the building reach 18 degrees Celsius? So when means that they're asking for a particular time when T of T is equal to 18. Okay, and that's related to this idea of the time constant for the building. So in the discussion in section 3.3, we see that this is our differential equation. This is heat generated by people and other things inside. This is either heat generated by a furnace or cooling generated by an air conditioner. And then we've got Newton's law of cooling. But people are leaving at noon. So we're assuming, and this is quite an assumption, that there's no heat being generated inside because the people are gone. We're also assuming that because the furnace has been turned off, that U of T is 0. So we are looking at just a Newton's law of cooling problem with M of T equals 14. And T of 0 equals 23 degrees Celsius is our initial condition. Okay, now you might say, well, what is this idea, this time constant for a building? What is that? That's also in section 3.3 in your book. So in section 3.3, they refer to that constant K in this way. They say 1 over that constant K from the differential equation that we were just looking at is called the time constant for the building. And what this is it's the time it will take for the temperature difference that's T of T minus M naught to change from the initial temperature difference, T naught minus M naught, to the final temperature difference, T naught minus M naught divided by E. And you might say final temperature difference, that's just over a certain period of time. The temperature is going to go from here to here. This is what we're using as our measure of a substantial change in temperature. This difference here is considered a substantial change in temperature. If you read substantial change in temperature or heard me say substantial change, excuse me, in temperature, and you said, what do you mean by substantial? This is what they mean by substantial. We had to find a way to quantify it. So we said, this is the time it takes for the temperature difference, T minus M naught, so that's the different temperature inside minus the temperature outside, to change from the initial temperature difference to this initial temperature difference divided by E. Well, that 1 over K is related to this K, that constant of proportionality in our differential equation that uses Newton's law of cooling. So when they say that the time constant for the building is 4 hours, what they're saying is that 1 over K is equal to 4 hours. And that is the time it takes for the temperature difference, T minus M naught, which in this case is T minus 14 degrees Celsius, to change from the initial temperature difference, which was 23 degrees Celsius minus 14 degrees Celsius, which is 9 degrees Celsius, to 9 degrees Celsius divided by E, where E is approximately 2.7. We're calling that a substantial change. We say, how much time does that take? Well, it takes 4 hours for that to happen. You say, okay, well, what does that mean for us? Well, if I know that 1 over K is 4 hours, then that means K is 1 divided by 4 hours. We can take the reciprocal of both sides. And we can substitute that into our differential equation. So our differential equation is now dt dt is equal to the constant of proportionality, K, which is 1 over 4, times the ambient temperature, which is 14 degrees, minus the temperature inside the building. And we have no heat generated inside because all the people are gone, and we turn the furnace off, so U of T is 0. And then we still have the initial condition. T of 0 is equal to 23 degrees Celsius. Okay, so now we have our mathematical model. And the question says, when will the temperature inside the building reach 18 degrees Celsius? Well, we have to solve this differential equation to figure that out. So we're going to solve the initial value problem, the differential equation and initial value problem to find temperature as a function of time. And then if we want to know when the temperature inside the building will reach 18 degrees, then we're just going to set the temperature equal to 18. And we'll solve for T, the time, the number of hours it takes. Now, if you want to, you can not use this 1 over 4. You can just use 1 over K and then change that later. I think that that actually might be a better way to do things. Actually, should we say 1 over K? Because this is actually equal to K. 1 over K is equal to 4, so K is equal to 1/4. I don't want to use 1 over K here. So I guess we should use 1 over, I want to use the time constant. So I'll call this 1 over C, where C is the time constant for the building. We don't want to use K in 2 different ways. So this constant K is equal to 1 over C. So let's find the answer in terms of C, and then we can substitute in K equals 4 for the first part because our time constant is 4 hours here. And then for the second part, we're solving the same problem, but our time constant is then 30 hours. So we can just change out C equals 3 and C equals 4 for the various parts of the problem. Okay, so first let's solve the differential equation. Well, this is separable. So I would divide both sides by 14 minus T and multiply both sides by dt. Then once those variables are separated, we want to anti-differentiate both sides with respect to the variable on that side. So I'll do a u substitution over here. If u equals 14 minus t, du is -1 times dt. So negative du is equal to dt. So that dt in the numerator is -1 times du. That's a u in the denominator. But it's in the denominator, so don't forget to put it over 1, or under 1, excuse me. So to anti-differentiate the left-hand side, we'd have to anti-differentiate -1 over u. So we get negative natural log of the absolute value of u plus a constant of integration. Over here, the antiderivative of 1 over c, is 1 over c times t when we're anti-differentiating with respect to t, plus some constant of proportionality, or not constant of proportionality, constant of integration. I'll call this constant c1. And don't forget to put u back inside. And then, of course, u was 14 minus t. Now, if I want to get rid of the -1 on this side, I need to multiply both sides by -1. So we'll have natural log of the absolute value of 14 minus t on the left equals -1 over c times t. -1 times that constant is just going to be a different constant. Now I'm not changing this 1 over c times -1 into a different constant because that particular c represents the time constant for our building. So I want to keep that time constant for our building in the equation. Still trying to get capital T by itself, so I will exponentiate to get rid of logarithms. These two functions undo each other. And we'll have 14 minus t over here. Its absolute value is equal to this. So I'll put a plus or minus on this side to account for the absolute value. And then this is e to a sum. That power is a sum. So I can think of this as e to the m plus n. Well, according to our exponent properties, e to the m times e to the n is e to the m plus m. Normally we see this with x's as the base, but now we've got the natural base e. We can use this in reverse as well. So this will give me e to the c2 times e to the -1 over c times t. And this plus or minus e to the c2 is just a different constant. So we have separated the variables, then we anti-differentiated. And now the rest of what we're doing is we're just solving for t of t. This I'm going to call C3. So we have 14 minus t equals C3 times e to the -1 over c times t. Trying to get t by itself. So I will multiply both sides by -1. So that'll give me t minus 14 on the left and -c3 times e to the -1 over c times t on the right. And then just add 14 to both sides. And if you want, you could say -c3 is equal to some constant c4. So we have this. Notice that that is our ambient temperature, that 14 degrees Celsius plus a constant times e to this power. And that power is related to the time constant of the building C. So when they ask us for the first question, when the time constant is, or if the time constant is 4 hours, T of T, that's the temperature inside the building, will be equal to 18 degrees when T equals blank. That many hours after noon, because T equals 0 corresponded to noon, right? And then they say when the time constant is 3 hours, because they left the windows open and then the time constant drops in that case, then the temperature inside the building will equal 18 degrees Celsius when T equals blank. So we're going to have a different time when that time constant is 3 hours instead of when the time constant is 4 hours. But notice that this still has an arbitrary constant C4 in it. In order to find the value of C sub 4, we need to use our initial condition. So we solved the differential equation by separating the variables, anti-differentiating, and then solving for T. And then we know that when T equals 0, the temperature inside the building is 23 degrees Celsius, because the temperature inside was kept at 23 degrees Celsius by the furnace until noon when the furnace was shut off. So this corresponds to this when little t equals 0, capital T is equal to 23. So we can substitute little t equals 0 here. E to the 0 is 1. So this is C4 times 1. So 14 plus C4 is equal to 23. So C4 must be 23 minus 14, which is 9. Okay, so our temperature is 14 plus 9 times e to the negative C1 times T. That's our temperature in the building as a function of time. Now we're going to use that to answer this question. And remember, the time constant is being represented by capital C. So this piece says that C equals 3, and this piece says that C equals 4. When C equals 4, this is what we have. Temperature as a function of time is 14 plus 9 times e to the negative 1/4 times t. And we want to know when is t equal to 18. Capital T equal to 18. So we just replace this with 18. And then we solve the exponential equation. It's like a college algebra problem at this point. So you subtract the 14 from both sides. And then you divide both sides by 9. And you want to get rid of the exponential. To get rid of the exponential, we take the logarithm of both sides. Those guys undo each other. And we have this. Then we'll multiply both sides by -4 in order to get t by itself. That's our exact answer, but let's see what that is equal to approximately. Natural log of 4 divided by 9 should be a negative number. We multiply that by -4, and we get 3.24. And we were asked to round to the 10th place, so that's 3.2 hours. Okay, and then they say, well, what if you change C to 3? What if you change the time constant to 3? Well, then that 4 would be replaced by a 3. So there would be a 3 here, and a 3 here, and a 3 here, and a 3 here, and a 3 here, which means that we would multiply both sides by -3 to get t. So it's going to be pretty much exactly the same solution method. You just replace the c with a 3 instead of a 4. So we'll still have natural log of 9, or 4 over 9, and this time we're going to multiply it by -3. And we get 2.4 hours. It makes sense. When the time constant drops, we would expect the temperature to drop from 23 degrees Celsius to 18 degrees Celsius faster. It's because all the windows were open. That's what they told us. I hope that helps you. In my class, I will include a sentence in the problem statement that will allow you to set up this differential equation. But as you're doing the homework, the expectation is that you've read section 3.3. So they are referring to this mathematical model, which they outline. They outline this mathematical model for you in the book. And then they say, okay, if the time constant is this, and you have to remember what the time constant is. Whoops, where did it go? Time constant is this. It's the time it takes for the temperature difference, the difference between the inside temperature and the outside temperature, to change from that initial temperature difference to that initial temperature difference divided by E. If you're saying why the initial temperature difference divided by E, it's just what we are choosing to consider a substantial change in the temperature. So we're saying that's substantial. That's our measure of substantial change, and it characterizes the building, and it's given by 1 over k, where k is the constant in that differential equation. So if the time constant is c, the constant of proportionality here, k, is equal to 1 over c. I hope that helps. Let me know if it doesn't. Talk to you soon.